at Tattoo Gardens, the build strategy is separate, independent structures. The utility shed came first. The structure I'm standing in front of now is the bathroom structure. It's actually 2 bathrooms, a shower and a sink, countertop in each. The toilets are composting and in separate, independent structures on their own. The title to this video is long. The off-grid part of the title means this structure is self-contained and independent, not connected to any utility services. The clean title means it doesn't pollute the air or the ground in any way beyond the materials used to make it. It uses rainwater that's heated by solar energy. And then if you use this shower, you're also using soap that we make here, made with olives and flowers and other plants that we grow here, turned into soap with lye in the soapification process. So what exits this building is nothing but natural stuff from the land and stuff from your skin and hair. Then it goes on to feed plants that Chalice has put in. I only know a few of them. There's all kinds of flowers like coffee and bananas and avocados, and that's Chalice's specialty. But what I do know that the output of this, instead of polluting the ground, ends up fertilizing breakfast. The luxury title is of course subjective, but the solid bronze faucet and shower fixtures that are washerless and they work good is kind of like luxury to me. And also, the hot water pipe is stepped out enough from the wall to work great as a towel rack. What that means is this towel gets heated, and heated towel racks to me smell like decadence and luxury. The mosaic tiling Chalice designed and laid with her children looks creative luxury to me too. This one is a gecko around neat leaves with bites out of them. The other bathroom starts with a snake on the floor, kind of like this gecko, but it winds around a palm tree on the wall where the shower comes out. But right now Chalice is working on a mud sink and countertop, so in order to see that, you're going to have to come and visit. The view overlooking a pond and native forest land doesn't suck either, so I'll stick with luxury. The goal achieved was no running costs, no utility bills, no effort to use. You just step in here and take a shower whenever you want, night or day, 24/7, year-round, and zero pollution. So in case any of what we've learned to create this helps you with your project, I'll share with you in this video how we collect our water, how we filter it and pressurize it, and then how we heat it to deliver it here. So here in northern New Zealand, you'd think the rainwater perfectly clean. Heck, weather systems just circle the South Pole without anything to pollute them. But for some reason, you know, the gunk that comes off this roof and around the plumbing here just is amazing. Stuff just must grow. And I was getting a hard time keeping up with changing filters and replacing filters, just a pain in the butt. So I simplified it to the point of not even having a screen at the top of this pipe here. It just flows straight down. Any leaves or bugs or junk goes straight down this pipe. And then I've got 2 pots here with a string so it easily fits in that hole. One is an old pot and this is a new pot. So basically all I do now is once in a while I'll just go and I'll replace an old pot with a new pot. And that'll collect any little debris gets collected by that pot. And I'll show you. Now I'm going to turn this into the new pot. Now at the front of the tank I'll just empty out this pot and clean it out. I don't know how many micron it is, but it's in the hundreds of microns, but it doesn't let any bugs or anything in, and it's really easy to clean. Pour the rocks back in. Now this is the clean filter, and that one up there will be the dirty one. So this is our first line of defense in infiltration of the rainwater. I just made the old pot now a clean pot, and we'll set it aside because now it's the new pot. The second line of defense in filtration is combined with pressurization. So you see those solar panels up there? They also, because we're in the utility shed, which is used to capture the water, the solar panels also power a well pump. So I connected the well pump in here, and it's actually floating. When it rains, I have a float switch on there, which goes and pushes this water from the middle, the clean water, up to a higher tank, which gives us good water pressure. I'll show you this setup. Very simple. Just a standard well pump, 24 volts, 24 volt system, and there's a float switch. So when the water gets high enough, it starts pumping up. And this water doesn't look that super clean on the bottom or the top, but it only collects water in the middle. The water in that tank up there is like crystal clear clean. I just connected that well pump to this because it has some vibration, so a little flexible hose at the beginning kind of seemed like a good idea, and then it goes into a more rigid hose before it feeds up the hill. So the water tank up there with the ladder on the right is the one we use for the rainwater. And it's got clean, every time I've looked at it, it's had crystal clean, clear water. Before it was up there, that tank was down below, so that the top of it was just below the bottom of this initial collector tank. And that suspension filter, it didn't need a pump because it was just pure gravity fed to that tank. And it was a really neat setup. So in case you have your main supply tank below your collection tank, I want to show you the old previous suspension filter we had because I thought it was pretty slick. So this is a good natural filter setup when you're draining below this initial tank, because the water comes into that outlet, but it has to go, this pipe here has a little bit of a hole there, like an air vent. So the water has to be up to that air vent before it'll actually flow in. So the end result is water doesn't come out of this pipe unless it's above the bottom and below the top. Put the tank as high as you can and use the fattest pipe you can from there. And then if you get a little bit too much pressure where you're using it, you can always go through a thin pipe for a while, a small diameter pipe, and that'll reduce it free and easy. That setup here with about 25 mil pipe down from 20 meters gives us about half of a city mains pressure to the bathroom, which is fine. Then after that tank, it flows through these filters. So this is an initial standard 5 micron filter. I checked it after a year and it was still clean like new. Then this is a carbon filter. This third one, which is unique, is Challis's idea. I never would have thought of it, but check this out. This filter does not filter out any sediment or particulate matter. What it does is a bunch of crystals, all these colorful crystals. What it does is add positive energy. So all the water after it's been cleaned gets energized. The water heating has no footprint. It's basically all on the roof. Water from the tank up the hill goes first to the square box on the right. This is a simple 80-liter thermal heater made of one long black pipe. Water enters the bottom and exits the top to feed an electric water heater tank below. So the wires coming down from the roof go right into this side here, and that one solar panel goes through this basically a simple charge controller, one battery, which feeds the the lights and USB ports, whatnot. And then the other 5 panels are wired directly through that thermostat and that heating element. Now let's discuss the challenge of connecting the solar panels to a heating element. These heating elements you can get in a variety of voltages and wattages. You usually can see them on the side there. Here's 12 volts, 600 watts. Another way to think of resistance is ohms. Ohms and resistance are the same thing. If you go to Wikipedia and search for ohms, ohm, OHM, you're going to get this list of formulas, very simple formulas based on power, which is same as watts, resistance, which is same as ohms. If you look at a voltage meter, it's that upside down U is the symbol for an ohm. Voltage, and then current, which is the same as amps. If you look at the back of your solar panel, you're going to see a table of numbers. Here's a few of them. Power, or watts, and then a couple voltages for when it's an open circuit or when it's got some resistance to it, and then you got your current. We can get one of the formulas from the Wikipedia page. Voltage times current equals power, or watts. So we can take our 18 volts times our 8.89 watts, or amps, and we can get 160 watts of power. That's some verification from our Wikipedia formulas. Here's a couple solar panels. Here's one sitting vertically over water. I've watched and observed these panels, what kind of power they're putting out with a voltage meter as the sun changes and conditions change. This one here, with the sun hitting the solar panel and bouncing off the water and hitting it double, will give you more than 9 watts, or 9 amps. I've seen the panel like this rated for 9 amps give more like 14 or 15 amps. It's kind of amazing. Then this one, which is slanted with the sun because it's not perpendicular, this will give maybe like 7 amps or maybe 8 amps at most under this angle. And then a cloud comes over and it'll change into like 2 or 3 amps, just like that. So you can go, if you go to a search for DC heating element, water heating element, you'll see all of these options. It really doesn't matter if you use an AC or DC heating element, but these high voltage AC elements aren't going to be so efficient, as we'll find out in a bit. You can get 48, 36, down to 12 volts, 24 volts in a variety of wattages. Which one is best depends on your solar panel setup, how much power you got. So we can do a little verification here. We'll come up with some resistance numbers that are going to help us in a bit. So from our list of, here we got voltage squared divided by resistance is our power. We can divide both sides of the equation by power or wattage and multiply both by resistance, and we change the formula around to be like this. So we can have our, here's the 230 volt element that came with the system, or just the tank that we're using, and we can say 230 volts times 230 volts divided by the 2 kilowatts or 2,000 watts, and we have a resistance of 26.45. That's the ohms. The heating element we're using now is 48 volts by 900 watts, and that comes up with a 2.56 ohms. That's the resistance. These ohms or measurements, these numbers are going to become helpful in a bit. You'll see one moment. If you can take your heating element and when it's not hooked up to anything, with a voltage meter on that ohm setting, like the upside down U, and hook it up, and you'll come up with a number similar to these. So this is a drawing of the solar panels we saw from the drone footage on the top of the roof here, and they're wired up. So one of them goes to the battery, and then the other 5 are wired up directly to the heating element in this 135 liter tank. So 2 of the 5 are wired up in series to double the voltage. We want 42 volts to get to this 48, closer to the 48 volt heating element. And then the other 3 are wired up such that, like, 2 of them are in parallel. So we go a plus to a plus, and then a minus to a minus. That gives us the same 21 volts, but it just doubles our amps. And then, so basically that's like just one big solar panel that we want to hook up in series to this other panel. So we have our plus wire goes into that minus, and then our minus wire goes into that plus, and that gives us our 42 volts. So in a sense we end up with 2 42 volt solar panels that we wire together and directly to this heating element, 48 volts by 900 watts. So how efficient is this setup? So we get another formula from our Wikipedia page, and we see in the winter, if we measure when the heating element is connected to the solar panels, within a couple hours of midday on a sunny day, I took a voltage meter and measured 27 volts. So this should be, when it's open, disconnected, we measure more like 42 volts. But when they're connected to the heating element, we're only measuring 27 volts. So we take our 27 volts, we square it, or multiply it by itself again, and then divide it by the ohm reading that we got here. 2.56, this is our ohms, and then we get 285 watts. So that says we're only really getting 285 watts to the heating element. Well, 285 is only 32% of our 900 watts. So I would call that 32% efficiency using that heating element in the winter. In the summer, we do the same thing, hook up the voltage meter to the heating element around midday, and we get 38 volts. Divide that by our same resistance, and we get 564 watts. That comes out to 63% efficiency. It's interesting, so these panels have the VOC and the VMP readings on it. So it's 43 volts if it's open, so that if there's no resistance to the solar panels, then you're going to measure 43 volts. But if you do get some resistance, you should measure only 36 volts would be the max. So it's interesting that we were measuring 38 volts here. I think a more efficient heating element would be a 36 volt heating element. The pre-thermal heater was the game changer. That got us over the hump in the winter to getting us 45 degree water. And that's only 100 meters of 32 mil black pipe. Put in a box that I painted black, and then I insulated it with this kind of bubble wrap, and then on the top where the sun goes in, there's this transparent, what is it, double wall polycarbonate. So it's not too heavily insulated, but it definitely works. I think it's more often people use solar panels and they hook them up through charge controllers to batteries and use an inverter. All those things suck up efficiency. So you look at these numbers like 32 and 63% efficiencies, and what I see is, well, okay, if you go through a charge controller, you're losing 10% or so efficiency. Battery charging and discharging, I don't know what kind of efficiencies you're losing there, but it's a fair bit. And inverters suck up another 10% or so efficiency. All those add up. Here, it's a very simple system. What's there to break? It's solar panels and a water heater. So this is the first time I've done it this way, heated water directly from solar panels. Next time around, it'll be a lot better. And this is what I'd consider. Hot water needs and time. We've got 135 liters in our insulated hot water heater tank, and then 80 liters feeding into that. So a little over 200 some odd liters of our heating system. We might get a cloudy day one or two days in a row, but you're going to get some power even on cloudy days. And I think, okay, so how much water do we need? We need, if we make our spigot wide open in the shower, we're going to go through 7 liters a minute. A little bit less, it's still fine at 5 liters a minute. So it's kind of like life. The more you spend, the more you need to earn. So how long the showers we're going to take, whether you use it wide open or not. You know, some people in some parts of the world they don't get showers, or maybe they'll use water and then when they're done rinsing their hair, they'll turn the water off while they're lathering up. So what your hot water needs and how long do you have to store it for is a relationship for how much you need to heat up. And so our pre-solar heater, I said, was a game changer for us. That got us working with the system through the coldest months of the year. So one thing I do more, so we have, in a sense, we have 2 water tanks. The pre-thermal heater, which is poorly insulated, and then the final heater, which is highly insulated. What if we had our pre-thermal heater, and then we had 2 of the 5 solar panels hooked up to say a 70-liter tank, and then that one fed, you feed it from the bottom, take out from the top, hot water rises, and then the final heater that we use would be the 3 solar panels going into another 70-liter tank. At the end of the day, we have the same amount of water storage, but this final tank could be more heavily insulated, and it'll be hotter water for instant use. And then there's formulas out there for all these heating elements and how long it will take to heat water, a certain quantity of water. But that's based on a consistent power source. Well, we're never going to get that in solar panels, so I never even bothered with that. Instead, I'd think about it more of a graduated heating system with increased insulation as we go. Another thing is I would optimize the solar panels for winter. So I would work on getting these numbers more in line, like maybe 50% winter and summer. So I usually think of mounting solar panels at the latitude we're at. Right now, I just mounted them on the roof here, which is on a 10-to-1 slope, so it's not efficient for winter or summer, but it's even less efficient for the winter than in the summer. So what I would recommend is optimizing the panels for winter. That would be something like even, say, a month before or after winter solstice, check the angle of the sun at noon. and use that. So then you'd be good within a few months of the coldest month of the year. Optimized for winter. Hope this helps. Keep having fun.